Okay, hello everybody. Thanks for being here. Thanks to Ludovic and everybody for the invitation. So today I'm going to talk about coalitional manipulation of voting rules, simulations on empirical data. It's a paper that will soon, quote, be published in the Constitutional Political Economy. And let's go. If my control works. Okay. So what are voting rules, what we are talking about? So roughly speaking, a voting rule is a function that takes some ballots as inputs and that will output one particular candidate as an output. The coalitional manipulability is the fact that in some scenarios, you may have a subset of the voters who can deviate from their sincere ballot and get a winner that they prefer to what would be the natural winner if everybody voted sincerely. For example, consider the following situation. So we have 36 voters who prefer candidate A to candidate C, candidate C to candidate B, candidate B to candidate D, and so on. 30 voters B, C, A, D, 24 C, B, A, D, and 10 voters D, C, B, A, for a total of 100 voters. So assume that you use plurality voting. So you consider that each ballot, in fact, just gives 1 point to the top candidate. Then candidate A will have 36 points. Candidate B will have 30 points, and so on. So candidate A will be declared the winner. But in fact, the two last groups of voters may realize that if they had voted for B instead of A, then B would have 64 votes. So B would win. And why is it interesting? Because in fact, all these voters prefer B to A. So they prefer these results. However, it's not ideal for them. It's still better than having B as the winner. Now consider the two-round system, which is the electoral system that we use in France. So you keep the two candidates who have the best scores, and then you iterate. So here, candidate C and candidate D will be eliminated during the first round. And then the two last group of voters during the second round, they would vote for B, and B would be elected. But here again, in fact, there is a possibility of manipulation because the first group of voters and the last group of voters may realize that if they upvote C in their ballots, then C will have the majority already in the first round, and C is going to be elected. And once again, it's interesting for them because they prefer C, the new winner, to what would be the natural winner of the election, who would be B if everybody voted sincerely. And then I will give a last example of voting rule. Here, instead of selecting only two voters for the next round, in fact, you eliminate only one voter at each round. So for those who were at the reading group this morning, is the rule called IRV that Emma presented. So here during the first round, D, who has only 10 votes, is going to be eliminated. These voters, their votes are transferred to candidate C. Then candidate B has the least votes during the second round. And these voters transfer their votes to C, and C is elected. And here it happens to be the case that, in fact, the situation is not manipulable by any coalition of voters. So you will need to believe me on that because it's not so easy to prove. So unfortunately, it's not possible to avoid this problem of coalitional manipulation completely because of the Gibbard-Sutter-Weiss theorem, which is a seminal theorem of the voting theory, essentially saying that any non-trivial voting rule is sensitive to manipulation. More precisely, any voting rule that is not dictatorial in the sense that it does not depend only on the ballot of one voter, and a voting rule that can also elect at least 3 candidates. If only 2 candidates are in the image of the voting rule, the theorem doesn't hold. But as soon as you have 3 candidates that can, in principle, be elected, then the voting rule will be subject to manipulation. So yeah, this is a very unfortunate result. So we cannot avoid manipulability completely, and all that we can try to do is to limit its scope. So in this paper, we are going to study wide variety of voting rules. For example, we have voting rules based on grades. So you have, for example, range voting, where voters put grades to the candidates. You have approval voting, where you can put thumbs up to a candidate. And it's allowed to put a thumb up to several candidates, but you cannot put 2 thumbs to the same candidate. In the same category of voting rules, you also have other ones like majority judgment, or another one that is called scoring, then automatic runoff. Then we also have the positional scoring rules. Here, the principle is that you give your preference ranking, and then this ranking will be put in front of a scoring vector. For example, 1, 0, 0, 0, 0, 0. And you will assign this number of points to each candidate. So the first one just corresponds to giving 1 point to your top candidate and no point to the other. So it's exactly the plurality that we saw before. But other examples exist, like, for example, Borda, where the scoring vector is linearly decreasing. We also have some elimination methods, like the 2-round system that I showed you before, and instant-runoff voting. And there are also other examples, like iterated versions of positional scoring rules that are called Baldwin, Hanson, Coombs, Kim-Rouge, and Vienno. Also, we have some Condorcet method. So to define what is the Condorcet method, I need to define what is the weighted majority matrix. So in this matrix, you will write how many voters prefer one candidate to the other. So for example, here you have 58 voters who prefer candidate A to candidate B. So that is immediately deduced from the profile of preferences, from the ballots. Here we are lucky. In fact, A is the Condorcet winner in the sense that A wins against B, against C, and against D. So it wins all its pairwise comparisons. And in fact, here it's even better because there is even a Condorcet order in the sense that if you remove the Condorcet winner, there is still a Condorcet winner, which is B, and so on and so forth. Unfortunately, it does not always happen. Here you have another scenario where there is no Condorcet winner, because in fact, A is defeated by C, B is defeated by A, C is defeated by B, and D is defeated by everybody, in fact. In that case, we can still define what is called the Smith set, which is the minimal subset of candidates who win their pairwise comparison against the other. So here, for example, in this example, the Smith set would be ABC. And when there is a Condorcet winner, of course, the Smith set is just reduced to the Condorcet winner. So what we call the Condorcet methods are the voting rules that elect the Condorcet winner when a Condorcet winner exists. So we have a whole benchmark of Condorcet voting rules that are named Copeland, Maximin, Black, Crank pairs, Schulz, and split cycle, and that just differ on what they do when there is no Condorcet winner. And finally, in the article, we also study a number of Condorcet variants of IRV. So IRV, you remember, we eliminate one candidate at a time, every time. But unfortunately, IRV does not meet the Condorcet criteria. So it's not a Condorcet rule. So there exist several variants that try to mix the kind of algorithm of IRV with Condorcet principle. The simplest one being Condorcet-IRV, saying, okay, you examine whether there is a Condorcet winner or not. If there is one, you elect her. And if there is no Condorcet winner, then you just run the usual IRV algorithm. But there are other variants that are studied in the article. Yeah.
Could you explain why, if there is a Condorcet winner, IRV would not find it?
So it's not an implication, but there are cases where IRV might not elect the Condorcet winner. In fact, there is a very, very simple case. Imagine that the Condorcet winner is second on all the ballots. Okay, then it will be eliminated during the first round. And it's easy to find example where the Condorcet winner is second on all the ballots.
Well, in your example, you were showing that you eliminate the single one which can have different score, but it's not true.
Yeah.
So what is the,
yeah.
what is the symmetry breaking?
Yeah. So in fact, it's a language shortcut. So any rule that would elect an element of the argmin of the score at each round could pretend to be called IRV. So in fact, in some sense, IRV is not a rule, it's a class of rule that respect this principle and that differ by the kind of type breaking that you mentioned. In practice, in the article, the election have a quite large number of voters generally, so the tie breaking rule does not matter a lot. Okay, so let's go for the experimental setup. So in the paper, we study two data sets. And in this talk, in fact, I will talk only about the first one, which is extracted from the Netflix price data set. So you have a whole lot of Netflix users assigning grades to a whole lot of movies. Of course, it's a very sparse matrix because most users don't put a grade to most movies. But what you can do is to extract some full submatrices of this data set. So we have a small algorithm to extract, in fact, disjoint full matrices of these data sets, and we have, at the end we extract more than 2,000 full matrices. And I will give more details on the size of these matrices in the next slide. And in the paper, we also use another data set, US elections that use ranked ballots. So not only people giving their preferred candidate, but generally there are 3 or 4 or 5 preferred candidates with their ranking. In fact, each data set has its own interest. I will start by the second. The second one, the interest is that it's a political data set. So it's very, very interesting to have preference on that can be related to real life political elections. But the problem with the second data set is that you don't know whether the ballots represent the true preferences of the voters, or if these ballots are already the result of a strategic behavior. And in that case, you don't have access to the true preferences. And the first one precisely has the dual pros and cons, in the sense that it's not a political data set, but there are more reasons to think that the information about the preferences is sincere, because as a Netflix user, you have an interest in giving reliable information to Netflix, because that way Netflix will give more relevant advice to you. Of course, no data set is perfect, especially in that area about human preferences. Very hard to have good data sets. So unfortunately, we have to do with what we have. And another quality of the Netflix data set is that it's a big data set for this kind of application. So in the end, here is the overview of the full matrices that we extract. In fact, we limit ourselves to matrices with at least 1,000 voters. And we take a number of movies from 3 to 11. 2 is not interesting because with 2 candidates, in fact, the question of manipulability is not interesting. And we limit at 11 because some of our algorithms, in fact, are not polynomial. And for computation time, it would be difficult with more than 11 candidates, sorry. Because generally, when it's not polynomial, the problem relies on the number of candidates. To examine manipulability, we use a Python package that we designed that is called Swamp, and which is specialized in computing the coalitional manipulability of voting rules. Another view of the algorithms that we use to determine whether a situation is coalitionally manipulable for a given voting rule. So for a number of voting rules, in fact, it's doable in polynomial time. So for plurality, for example, it's very simple to test whether the situation is manipulable or not. For a number of them, we use an approximate algorithm that runs in polynomial time, and it's really an approximation scheme in the sense that generally it computes the minimal number of manipulators that is necessary to manipulate, and there is a guarantee on the factor between the number of manipulators that it finds and the number of manipulators that is necessary. For some others, and in particular for IRV, we use an algorithm that is exact but not polynomial. And for IRV, for example, it's in factorial of the number of candidates, essentially because you have to examine all the possible elimination path of the candidates. And for some other voting rules, we use some heuristics that may be polynomial or even not. And when you use heuristics, in fact, in the end, the result is always of the same kind. Generally, in fact, we have 2 heuristics. One heuristic that is specialized in trying to prove that this situation is manipulable, and one other heuristic that is specialized in trying to prove that it's not manipulable. So when one of them is able to conclude, then we can say, okay, the situation is manipulable. I know it's proved, or it's not manipulable. I know it's proved. And when none of the 2 algorithms is able to conclude, then we have no choice but to say, okay, in this situation, we don't know. So before going deeper into the question of manipulation, the results about manipulation, I will give a few clues about the qualitative features of the profiles, which is independent of the voting rules. It just pertains to the preferences of the people themselves. So in fact, having a Condorcet winner appears to be a very frequent phenomenon. In fact, it appears in close to proportion 1 of the profile. And even having a Condorcet order, in fact, is very frequent, more than 95%. And there is this other notion that is called resistant Condorcet winner, that essentially shows that a situation where there is a Condorcet winner and it will not be manipulable in any Condorcet voting rules. And this is a much rarer phenomenon. And in fact, we will use it later as an upper bound of the manipulability for the Condorcet voting rules. And the last one, majority favorite, is just a candidate that is the top candidate for more than half of the voters. And this is quite rare. Okay, so here I would say that this plot is the main result of the paper. So for each voting rule, we compute its CM rate, which is simply the proportion of profiles in which it is manipulable by a coalition. So it's sometimes the probability that the voting rule is manipulable by coalition. Here in blue, we have 7 rules that I usually call the IRV family, in the sense that there is IRV itself and some variants of IRV, and in particular, all the Condorcet variants of IRV that I mentioned earlier. You can see that the CM rates are very low, lower than, say, 5%. And for the other rules, I should explain how the plot should be read. For example, for this rule, Baldwin, you see there is a blue bar, which is the proportion of cases where Swamp was able to certify that the profile was manipulable for this voting rule. On the top, above the black line, it's the proportion of cases, the proportion of profiles when it was proven non-manipulable. And in fact, the black bar, thin black bar, corresponds to the case where Swamp was not able to conclude about manipulability. So of course, for some voting rules like plurality, where we have an exact algorithm, there is no black bar because there is no uncertainty, algorithmic uncertainty. But for some voting rules, we are left with some uncertainty. But anyway, despite this uncertainty, it's enough to tell that IRV and the others have very better results than all the other voting rules.
I have a question.
Yeah.
With respect to the slide, there are some algorithms for which you have only heuristics.
Yes.
So is there any case where you don't have a conclusive result in the algorithm? That is, you cannot compute it's manipulable, and you cannot compute it's not manipulable.
Yeah.
Both take a lot, both take too much.
In terms of time, or
since it's a heuristic, it does not necessarily terminate.
So maybe I don't use the right word, or I didn't explain well. So in fact, so what it does exactly is that, for example, for Baldwin, we have, in fact, it's an algorithm that is able to test. You have one algorithm that is able to test a necessary condition of manipulability, and another one that is able to test a sufficient condition of manipulability. And that's it. So I don't know if you want to call that heuristics or algorithm. But say anyway, this algorithm will terminate. They will give you a result. And if you're in the case of the sufficient condition or the necessary or the negation of the necessary condition, then you know what you want to know.
Those two conditions are
yeah, do not cover all the profiles. Exactly. Exactly.
So it could be that,
exactly. And that's precisely why you have these black bars that correspond to the cases where the algorithm that tries to certify manipulability was not able to do so. And the algorithm that tried to certify non-manipulability was not able to do so.
okay, so that the black line.
That's exactly the black line. Yeah. Yeah, François.
Perhaps I missed that but so this is the setting, right? With the number of candidates and uniformity rules on the choice of candidates to get these proportions. I mean, you need a stochastic
Okay, so yes, more or less. So in fact, the only probabilistic setting that you have, quote, is just drawing a profile at random among the 2000 something profile that we have. But in fact, what we do is that we just do the job for each of the 2000 and so on profiles that we have in our data set. Okay.
But in a sense, if you have uniform, you have this profile. It's not like only a combinatorial setting. We have a size of a population.
No. Here we really have a data set with 2000 something profiles, and for each profile and a given voting rule, we say, okay, the natural winner is this candidate, and does there exist another candidate and a subset of voters such that this subset of voters can and want to manipulate in favor of these challenger candidates.
But I thought that this 2000 something were matrices, not profiles.
Yeah, that's a synonym in my mouth. So, so more precisely, in the case of the Netflix data set, what you have is that you have a matrix of users assigning grades to movies. Okay, but that induces a ranking of the user over the movies.
Yes. But,
okay. So here I am cheating a bit.
Let's say that you have a big matrix of user, all sci-fi movies.
Yeah.
And then there will be another genre of movies with different voters.
Yeah.
So,
yeah, but
what is this proportion corresponds to? Every matrix in the data set?
No. It corresponds to the particular way that we extracted these matrices from the data set.
Maybe what you can say is that you have a weight one for each matrix.
Yeah, but it's true. What I think Sebastian wants to points out is that what is true is that our result somehow depends on the way that we have chosen these submatrices from the big data set. And in fact, the way we do it, I could explain the algorithm for that extraction. Tends to extract communities, in fact. But it's normal because you want a set of movies and a set of voters, such that many of these voters, such that all of these voters have rated all of these movies.
Yes.
So,
but for two different matrices, maybe the community votes differently.
Yeah, maybe.
Everybody agrees with some genre of movies, and maybe the people agree less in some other genre. And then maybe in one matrix it's more manipulable.
Yeah, sure, but I would say that it's a good thing for the data set that you are looking at if you have a diversity of situations. And by the way, excuse me, Ellie. And by the way, the fact that you extract community, I think it's a good thing. So the way we proceed, in fact, tends to put together, let's say, I don't know, romance movies and karate movies and so on. But I think it's a good thing because yourself as a user, it's very difficult for you to compare on the same range of grades movies that are totally different in genre. So the day where you want to watch a blockbuster and the day where you want to watch an independent film, in the end, if you want to put a grade to the two, it does not necessarily mean that you prefer one to the other. But when you put a grade to a karate movie and a grade to another karate movie, it's more defendable to think that you prefer one to the other. So I think it makes sense, in fact, to extract submatrices this way. Ellie, sorry.
And that's why you mentioned at the beginning that you get the group of voters for each submatrix disjoint. So that
in fact, the group, no, sorry, I was not clear. The groups, so for a given number of candidates, the subset of movies are disjoint. So for example, if you take all the submatrices that I took with 5 movies, the sets of 5 movies are disjunct.
And the set of voters?
Not necessarily.
Not necessarily.
Daniel?
I don't think, I'm not sure it's a good question, but just to check if I understood correctly. What happens if you take one of these sets where everyone has seen all these pictures, movies, sorry, and you take a subset?
Yeah.
Are you going to have the same percentage? Because of course a subset will have will validate the rule of everyone has seen every movie.
Not necessarily.
Not necessarily.
Not necessarily.
So it's more than sensitive to the way you choose, because even if you have your approach for choosing the community, even inside the community, a subset of the community can have a different result, right?
Yeah, sure. So in particular, to take an extreme case of what you say, if inside the community you take all the voters who prefer movie 1, so of course movie 1 will win and it will not be manipulable. Essentially, no, but just to say that in principle, of course it's true.
And this is where I was trying to introduce some randomness in the story to characterize the set, because if not, it's very, very sensitive to the way you select the.
Yeah.
And I had another question. Somehow it's sorry.
At this point, maybe on this point, what did you try also to change the order in the matrix in order to get similar data set, similar in characteristics, but not
no,
and to check if you get the same kind of results?
No. What is true is that in fact these kind of results, and this is where also the second data set comes into play, are in fact very robust to the data set that you take. So when you take a political data set that comes from totally somewhere else, in fact you have exactly the same kind of results. And for me, that's the most convincing.
Another question is that what you are evaluating, which is of course the critical importance, is whether the vote is manipulable or not.
Yeah.
But in order to be, if it is manipulable, in order to manipulate, you need these people to talk to each other.
Yes.
So is there a way to model the game theory approach? You know?
Thank you, Daniel, for this excellent transition to my next slide.
Maybe I can ask a question before that. So here you have between 3 to 11 candidates.
Yeah.
Did you try to make these figures for 3, 4, 5, 6? There are some evolution, in particular for the IRV family. Yes,
for this one exactly no, but for another figure, I will answer positively to your request. So now this is related to Daniel's question. Here is now we consider a particular notion of manipulability where all the manipulators use the same ballot. So it's a kind of manipulation that is easier to coordinate because maybe you will need to think carefully about the ballots that you need to use to manipulate. But once you've done that, you can just broadcast the information and all the concerned voters can apply this strategy. And by the way, it has an additional advantage for us that's much simpler to compute. So we have more precise results. So the main difference maybe is that for the 2-round system, which is the usual French system of the presidential election, the results are much better than in the general case. In the general case, we were above 40%. And also for another rule that is more strange, that is called veto. But for the other rules, it's still very, very bad compared to the IRV family.
IRV also, we see that it's very low.
And for IRV, it's even lower than before. And for the Condorcet variants of IRV, it's extremely, extremely low. Another similar idea is what we call trivial manipulation. Essentially, the idea, at least for the ordinal voting rules, is that you when you want to manipulate, you say, okay, the natural winner is W. I will bury W at the bottom of my ballot. And then if I want to make win the challenger C, then I will upvote C at the top of my ballot. It's a very simple manipulation heuristic. And in that case, also, all the IRV family behaves, of course, very well, because anyway, it's lower than the manipulability rate. All the other ones tends to behave quite badly, except once again, in particular, Durand and Leto. I don't remember what well, okay. Something that is related to that is what I would call the CM complexity index. Intuitively, the idea is to say, okay, conditionally on the fact that you are in a manipulable situation, how difficult is it to compute this manipulation? So it's a very simple indicator saying, okay, what is the probability that the profile is not UM and not TM, so not unison manipulable and not trivially manipulable, conditionally on the fact that it's coalitionally manipulable. So, for example, for the two-round system, it's close to 1, meaning that, in fact, when it's manipulable, it's very rare that it is a unison manipulable or trivially manipulable. In fact, this plot is not very convincing, to be honest. Because we have big uncertainty bars at places where we wouldn't want to have ones. And in particular, we cannot compare, for example, Tideman, which is one of the IRV variants, with, for example, Baldwin. So I will just show you what happens with the other data set, and that will be the only place in the talk where I will talk about the other data set. Where the results are a bit clearer, and essentially the ones that have a high CM complexity index are the IRV family with an index that is around 80% or more, and once again Durand and Vito. And for Baldwin, we don't know, and for the other ones, it's significantly lower. So, in fact, there always is a proportion of case where the rule is manipulable. No rule has a CM rate of 0, so this rate is always defined. Does it answer your question?
Yes, but from the previous graph, I have the impression, for example, that the first 4 or 5 here.
Yeah.
What is the number of configuration?
Quite low. Yeah, so you also have not only an algorithmic uncertainty, but also an uncertainty of sampling because the sample is relatively low in that case, unlike for the other plots. That's a good remark. Then we examine the average ratio of CM winners because even in a situation where the voting rule is manipulable, it can be manipulable in favor of one challenger candidate, but there could also exist another possible manipulation in favor of another challenging candidate. So it's not exactly the same if there is only a manipulation possible in favor of one candidate that is different from the natural winner, or if it's possible, say, for all the other candidates that are not the natural winner. So that's what we represent here. So it's the expectations. So considering a uniform drawing on the profile of the data sets, the expectation on the proportion of candidates who are not the natural winner, but who can benefit from a coalitional manipulation nevertheless. Of course, for the IRV family, it can only be very small because we already know that only the fact of being manipulable is very rare. So that's it. But for some other rules like range voting, so range voting with the little grades, it's close to 1, which means that typically, not only is it manipulable, but in fact, it's manipulable in favor of any other candidates that is not the natural winner. And precisely for that graph, I think it's interesting to try to see what differs depending on the number of candidates of the election. So here, I put only a subset of the rules, namely the rules for which the black line is reasonably small, so less than 1%, because since it's a line plot, it would have been difficult to represent uncertainty and so on. So I only represent rules for which we have almost exact results. Here, so in the x-axis, we have the number of candidates of the election. And on the y-axis, we have the average number of candidates who can benefit from manipulation, and which is by nature bounded by the number of candidates minus 1. So for these guys of the IRV family, essentially it's 0, whatever the number of candidates, or close to 0. And for most of the other voting rules, it seems to be relatively linear. And for example, for plurality, when you have 3 candidates, it's generally manipulable in favor of 2 of them, and when you have 11 candidates, it's manipulable in favor of 10 of them, and so on. And the main exception to that observation is the 2-round system. So the 2-round system is in brown, and in fact, it starts at 0. Which is not surprising because when you have 3 candidates, the 2-round system is equivalent to IRV. So in fact, the 2-round system is relatively good when you have a few candidates, but when the number of candidates increases, in fact, for 11 candidates, the average number of candidates who can benefit from manipulation is around 8.5, something like that. So it begins to be very bad. Just a look at the clock. Then we examine the Condorcet violation rates. So you remember the Condorcet principle consists in saying that whenever there exists a Condorcet winner in the profile, it would be desirable to elect her. So we are looking at the proportion of profiles where the rules elects the Condorcet winner conditionally on the fact that there exists one. In fact, conditionally or not does not change much because if you remember, in fact, almost all the profiles have a Condorcet winner. So in blue, we have what happens with the sincere election where everyone votes, just cast their preferences as their ballots. And of course, for voting rules that complies to the Condorcet criterion, like Maximin or Schulz, for example, the blue bar is of size 0 because they cannot fail to elect the Condorcet winner by definition. For IRV, for example, there is a small proportion of cases where IRV misses the Condorcet winner. So even if IRV does not meet the Condorcet criterion in theory, in fact, you see that the rate of violation is quite low. In fact, it's close to, I don't know, 2% or something like that. For the Condorcet variance of IRV, of course, the blue bar is non-existent. And then in orange, we represent what happens taking into account the manipulation. So the rule may fail to elect the Condorcet winner, either because it fails to elect the Condorcet winner naturally, or because there exists manipulation that elects somebody else than the Condorcet winner. And in fact, when you take that into account, even the classical voting rules like Maximin, Schulz, split cycle, Vienno, and so on, they have in fact a very bad Condorcet violation rate because they are often manipulable in favor of other candidates. On the contrary, with IRV and its variants, even taking manipulation into account, you don't miss the Condorcet winner very often.
That's clear.
Yes.
The probability that there is the Condorcet winner is with the manipulation or without the manipulation?
So in the orange case,
Yes.
okay. So to saying that you violate the Condorcet criterion in the orange case means that either you don't elect the Condorcet winner sincerely, or that you are manipulable in favor of another candidate. So,
that does not mean that once the ballots have been manipulated, there still exists a Condorcet winner.
No. The candidate that is of interest is the true Condorcet winner, and you want to know whether you will elect her or not. And another way of saying that is that you consider that the set of potential winners is the natural winner and all the candidates that can benefit from manipulation. And you say that it will be Condorcet compliant despite manipulation if this set is exactly the singleton of the Condorcet winner. Emma, sorry, you had a question? The same question. Similarly, we have on the same principle, we examine the loss of normalized social welfare. So here, remember that, in fact, we do not have only rankings on the movies, but in fact, we have grades. So we can say that these grades somehow represent the utility that the voters have for the different movies. And say that the total utility of a movie is the social welfare associated to this movie. And for each candidate of the election, you can compute its normalized social welfare as the renormalized on the scale going from the minimal, the worst candidate to the best candidate. Once again, we have two variants of that, the sincere one. So it's interesting to see that, in fact, in terms of sincere voting, the consequences of the election on the social welfare are, yeah, let me rephrase this. The consequences of the choice of the voting role on the social welfare, in fact, is not very big. You see that for most voting rules, the loss of social welfare, in fact, is very low compared to one, except maybe for plurality, which is one of the worst ones, and maybe veto, let's say. But it also means that even when the rules fail to elect the Condorcet winner, in fact, generally they elect a candidate that is really close in terms of social welfare. But here again, taking manipulation into account, only the IRV family behaves reasonably. And this will be my last plot. So here is a notion that I really want to underline. So the idea is to say that one of the big problems of the manipulability is not necessarily that people will indeed manage to coordinate, organize the collective manipulation at a big scale, and so on and so on and so forth, but also that the voters that will behave strategically will have de facto more power than the voters that behave naively, sincerely. And that by that, you break the principle one person, one vote of equality between the voters. So on one side, you can have voters that are strategic and also that have good information about what the other will do, because that's also necessary to design a good manipulation. And other voters that are less strategic and or having less information on the landscape. So this is what the CM power index tries to capture. So intuitively, if the CM power index is equal to X, it captures the idea that a strategic voters has X times more power than as much power as a sincere voter. So how do we compute that? So imagine that you have your election with a given voting rule, the winner is W, and you examine the manipulation in favor of challenger candidate C. Okay, so you can split the voters into two parts. The one that prefer W to C, and these one are going to stay sincere because they prefer W anyway, so they don't want to change their vote. And the other ones are the ones who prefer C to W and who are potential manipulators. Okay, so these ones, just remove them for the moment. Just keep the sincere one, and then you will try to add manipulators. You add strategic ballots as many times as necessary as to be able to make C win. Okay, so for example, I assume that you had 60 sincere voters, and imagine that you see that with just adding 30 strategic ballots, you are able to make C win. In some sense, it means that a strategic ballot is twice more, as powerful as a sincere ballot, and that exactly that we compute. And in fact, so we do, I don't remember if we do an average or a max or a mean over the different candidates, but that's the intuition. So for the IRV family, this CM power index is in fact very close to 1, which is not surprising because generally you cannot manipulate, so you don't have enough manipulator. And it's trivial to see that if you have more manipulators than sincere voters, you can indeed manipulate. So the CM power index for this kind of voting rule cannot be lower than 1. But for some other voting rules like range voting or approval voting or star, it can be close to 5 or 6, which is just enormous. Yeah. In fact, because at the time where I did this article, so it's 1 year and a half now because of the time in journals. In fact, Swamp was not very well optimized for some rules to compute exactly that, the minimal number of voters. And typically because of historic reasons of how the package was programmed, it was specialized in knowing whether you could manipulate with the number of manipulators that you had. And typically saying, okay, if I can, then I know that the minimal number of manipulator is lower than that. And if I cannot, it's bigger than that. But it's not a very precise information. But it's a bit better now. For most of these voting rules, it's a bit or much better for many of these voting rules. So if I computed these plots today, I think they would be more precise. So, for example, as a consequence, for example, for a Bucklin rule, we don't know. We know that it's not as good as the IRV family, but we don't know to which extent it's worse. So, in conclusion, I think that you gathered already that IRV and its variants are much more resilient to a coalitional manipulability than essentially all the other voting rules of the classical voting rules of the literature. And also, I did not mention it, but you saw it in the plots, that the differences between the rules of the IRV family seem very, very small. We have a few theoretical clues about that. For example, we know by theory that the CM rate of Condorcet-IRV is lower than the one of IRV, which is itself lower than the one of another variant that is called exhaustive ballot. But for the other rules of the family, we would need more precise algorithms or theoretical results to distinguish them. For the future, so it's a bit the days of the future past, because as I mentioned, I did this work one year and a half ago, and some of this future work, in fact, is already implemented. The improving the CM algorithms in SWAMP, especially to reduce the uncertainty margins for the concerned algorithm. And in fact, for some of them, it has already been much improved in the meantime. And in particular, we improved the CM algorithm for Baldwin, Copeland, Kemeny, Kimrush, Nansen, Rangper, Split Cycle, and Vieno. And we also implemented two new rules that are called K approval and Slater. And that's it. Thank you very much.
Any question in the room?
Yes, that has nothing to do with your talk, but in general, about evaluation voting and mechanism. In addition to being manipulable or not, I have the feeling that there is always a subjective issue with voting, right? Because like in society, we prefer the guy in general, the elected is the one that got the maximum right for the maximum number of people. Others will prefer that known, if there is one person that one voter that doesn't want at all a certain person, it will not be elected, so on and so forth. This is very subjective, it depends on the society. So how can you evaluate what is a good voting approach where it depends so much on a subjective stuff?
Yeah, in fact, the problem of voting theory, contrarily to what happens in auctions, for example, is that essentially you don't have a rule that satisfies all the good properties. What us as scientists can do, all that we can do, is just to shed light on what properties do the different rules have. And then say to the social planner, to the political decider, okay, if this property is more important for you, then you should have a look at this rule, and if that other property is more important for you, you should have a look at this other rule. But yeah, at the end of the day, it's a political choice. It's, in a broad sense. Even in non-political context.
Is that being taken into consideration by the people that are deciding about voting rules in different countries?
I would say more and more, in the sense that, for example, nowadays in the US, there is a growing movement of implementing alternate voting rules in several locations. And this movement is very much influenced by groups of people who have really looked into how the voting rules work. And so recently, for example, the approval variants of approval voting have been accepted in the town of Fargo, North Dakota, in the town of St. Louis, Missouri. There are also IRV, which is already used in several countries like Australia, is more and more used in the US, for example. Now it's used it was already used in the city of San Francisco. Now it's used in the state of Alaska, statewide. So historically, for example, in Australia 1 century ago, I don't know how it happened exactly to choose this voting rule, but nowadays, it's really advocated by people who have really looked into the properties, the theoretical properties of this rule.
Because it's a key democracy issue, right?
Yeah, sure. Yeah, sure. Yeah, sure. Yeah, sure.
The properties of the process that they're using to rule.
Yeah, sure. And in that sense, the example of the US is very interesting, especially compared to France, because in the US it's very decentralized. So it's very easy for, let's say, just a city, for example, to say, okay, for our mayor election, we will use this voting rule. And you don't have to say, okay, for all the cities of the countries, we are going to change the rule, which is a very very risky choice in some sense, and that's what we would need to do in France if we would want to experiment. We don't have this opportunity in France, considering the way that we work, to do this kind of local experiments. And so it's very easier in the US because some state will try one voting rule, some city will try another one, and then a few years later you can see if they are happy or not. Essentially. Yes.
You say a few words about game theoretic extension of that, because I mean, here, if I get it correctly, you have this say initial sincere thing, and then people react to that. The Condorcet.
Yeah.
But if I were the, I mean, you could say that the first way that people will think about their ranking would be already taking down. So,
sure.
Are there game theoretic formulation of this, like this equivalent of this stable marriage or things like that, which would take the
yes, yes, but in general they are either too complicated or not interesting. So I will explain what I mean. So, for example, the most natural question from a game theoretical point of view would be to say, okay, once I have a profile of preference and a voting rule, in fact, it implicitly defines a game. We have a game with a preference of the players over the possible issues of the game. And so usually in vote, we look at pure strategies. We don't have a look at mixed strategies. It makes more sense. So one question would be, does there exist an equilibrium of this game? So if you just have a look at Nash equilibrium, in fact, it's not interesting because in a large election, almost any situation will be a Nash equilibrium. Because if you just change your ballot, most of the time you won't change the result of the election. So unless you're very close to a tie, in fact, any situation is a Nash equilibrium because your ballot, in fact, doesn't change the result. So you don't have an incentive to deviate, or you can deviate or not, nobody cares, essentially.
Because of the size of the problem.
Yeah, because so you have large regions of the space where the result does not change, and small frontiers, and so in most of the case, in fact, the notion of a Nash equilibrium is not
coalition.
So yes, so that's the next thing. So then you have strong Nash equilibrium when you have a look at a coalition of players. So it's very related to coalitional manipulation. And in that case, in fact, for most voting rules, so there is a small condition, but for most reasonable voting rules, if there is a strong Nash equilibrium, the winner is necessarily the Condorcet winner. So there necessarily exists a Condorcet winner, and vice versa. If there exists a Condorcet winner, then there exists a strong Nash equilibrium.
But then why don't people use that?
So because essentially, if you do that, what you would conclude is that for essentially all the voting rules, all the reasonable voting rules, for a good notion of reasonable, okay, they all behave quite well, because when there is no Condorcet winner, there is no equilibrium. Why not? And when there is a Condorcet winner, they will magically find it, because it will be the only equilibria of the strong Nash equilibria of the game. But in practice, it does not happen that way, because if you do a plurality vote, it's very rare that people are sophisticated enough in their behavior to find these strong Nash equilibria.
Okay, but you could compile the definition preferences into an equilibrium of strong equilibrium, and people will give their votes in a certain way.
Yeah.
And compile, if you find this strong equilibrium, that and declare the winner that way, which would be the Condorcet one.
You mean to implement that as a voting rule?
Yeah.
Which essentially amounts to say that you just implement a Condorcet voting rule. But it would be sensitive to coalitional manipulation nevertheless anyway. But another way of seeing the problem is why is this notion not so interesting? Is that if you use this notion of strong Nash equilibria, it will not allow you to compare the voting rules. You will say, okay, plurality, okay, it elects the Condorcet winner every time that there is one because it's the only strong Nash equilibrium. Baldwin, the same. IRV, the same. But in reality, it does not happen that way. It's not. You will not be able to make a difference between the different voting rules if you use that notion. Reasonable voting rules, for a good notion of reasonable. For all of them, you will say, okay, they have this equilibrium on the Condorcet when there exists one and no equilibrium in the otherwise.
So what you say is that if there is no Condorcet winner, then there is no Nash equilibrium, strong Nash equilibrium.
Yeah.
That's what.
Yeah. So for all these class of reasonable voting rules,
even in the extent mixed sense, it's just because you look at pure.
probably so. If you look at mixed strategies, it's a bit more complicated because in that case, the result of the game will not be a candidate, but a distribution of the candidates. And then you need to have the to know if people want to manipulate or not. You need to have in your model what are their preferences on the distribution of candidates. Okay. So if I only know that if in the model there is only the fact that you prefer A to B to C, I don't know, for example, if you prefer 50-50 mix of A and C or having D for sure, for example. So you can do things, but you would need to have preferences on von Neumann-Morgenstern utilities and stuff like that. So you put the finger in other machinery. Yeah.
Are there questions on the bridge? In the room? Thanks again.
Thank you very much.